Welcome everyone to a trip around the world to discover innovative approaches to informatics challenges associated with biological data. If I had been thinking ahead, I might have shortened that just a bit. My name is Abby Benson. I work for the U.S. Geological Survey, and I'm the U.S. Node Manager for the Ocean Biodiversity Information System and the Global Biodiversity Information Facility. I'm also the co-chair for the ESIP Biological Data Standards Cluster, along with Robert McGuinn, who is here today and will help me moderate the chat, and Aaron Satterwhite, who couldn't be here today. Our note taker for this session is Matt Biddle from IUSE, but anyone is welcome to take notes if you want to. I think the link to the notes is in the chat if you want to do that. I'd like to take a moment to acknowledge the indigenous lands of the Cheyenne that I am currently speaking to you from and highlight the indigenous knowledge and understanding of biological and ecological systems that is vital to our understanding today. Please note that by participating in this session, you agree to adhere to the ESIP community participation guidelines, and any issues can be reported at the link in the agenda. Also, this session is being recorded for future viewing. Please stay muted and turn your cameras off if you're not speaking, and you can post your questions in the chat. Also, during Q&A and the discussion section at the end, you can raise your hand using the raise your hand feature under the reactions options. We would appreciate it if you could record your name, affiliation, and location in the notes document for this session, or you can add it to the chat. So, the goals for our session are to explore innovative approaches to biological data informatics, build linkages to the Biodiversity Information Standards community, also known as TADWIG, and to foster knowledge sharing between biodiversity data managers nationally and internationally, and build a community of practice around biological data standards within the United States. So without further ado, first up we have Nicole Kearney, Manager for the Biodiversity Heritage Library Australia, who will talk to us about how the biodiversity community are making historic literature discoverable online. So just give me a second to get that recording up.
Good morning, everyone. I'm saying good morning because it's 3 a.m. here in Melbourne, Australia, which is why I'm not awake to give you this talk in person. I'm Nicole Kearney, and I would first like to acknowledge the traditional custodians of the land upon which I work, the Boonwurrung and the Woiwurrung peoples of the Eastern Kulin Nation. But I would also like to acknowledge the Indigenous peoples across the whole of Australia, because that acknowledgement is missing from the historic literature I work with. These illustrations are all from the late 1700s and early 1800s. This is the period in our history when these animals were being discovered by Europeans. The publications contain no acknowledgement that there were already a people on this land who had an intimate knowledge of the biology and the behaviour of these animals. Australian animals were unlike anything that the Europeans had ever seen. But of all of Australia's animals, they found the platypus the most bizarre. It had fur, which made it a mammal, but it also had webbed feet and a beak like a duck. And weirdest of all, it laid eggs. It didn't fit with the Europeans' understanding of the animal world, and so it changed everything. The historic literature about the platypus is hugely significant, but it's also really hard to find. And I'm going to talk to you today about why that is and what we've been doing in the biodiversity community to make that historic literature discoverable online, using retropids. So what's a retropid? A retropid is a retrospectively assigned persistent identifier. Now, I believe that's a new term. Pretty sure it's a new hashtag, and I'm hoping it catches on. In this talk, I'm hoping to convince you of three things. The first is that the historic literature is still hugely relevant today. The second is that the historic literature should be open access, particularly that historic literature that is in the public domain out of copyright. And the third is that the historic literature desperately needs retropids, retrospectively assigned persistent identifiers. To make my argument, I'm going to take you on a journey back in time. We're not going very far to begin with, just back to the 1970s, the home of all things retro. If you wanted to read a journal article in the 1970s, you had to go to the library. And there on the shelf would be all the articles published that year and that decade, and around you on the shelves below and beside you would be all the other articles published in the journal you were looking at, all the way back to the beginning. In this case, all the way back to 1868 for this journal. Scientific knowledge at your fingertips. Now, I was born in the 1970s, but things were pretty much the same when I was at uni in the 1990s and early 2000s. It took exactly the same amount of effort to find a modern article as it did a really, really old one. Things have changed. This piece of information, the announcement of a new species of seahorse, popped up in my Twitter feed, and I was interested in this. And there in the tweet was a digital object identifier, a DOI, in the form of a clickable link, which means that I could click directly through to the primary literature and read all about this new discovery. And if I wanted to know more about pygmy seahorses, I just had to scroll down to the reference list. And there are a whole lot more digital object identifiers allowing me to click through and read all the other papers cited in that article. A never-ending chain of knowledge. But there are gaps in that reference list. There are DOIs that are missing, and that keeps me awake at night. Because now that it's so extraordinarily easy to find and read recently published articles, researchers are much more likely to read and cite the new stuff. The historic literature is in danger of falling into obscurity. And I really care about this on a personal level, but also a professional level, because I manage the Australian branch of the Biodiversity Heritage Library, which is the world's largest virtual library of biodiversity literature. It's a global consortium of over 500 libraries around the world, digitising their biodiversity heritage literature and making it accessible online. Together, these 500 plus libraries have digitised more than 59 million pages, and there's information in those pages on millions and millions and millions of the world's species, and it's all openly accessible. But that's not enough, because accessible does not equal discoverable. The vast majority of the historic literature lacks DOIs, and thus it sits outside that linked network of scholarly research. If we want the historic literature to be both discoverable and persistently citable, it needs digital object identifiers. And so last year I started a persistent identifier working group within the biodiversity community. And our role is to bring the historic biodiversity literature, that foundation of all biodiversity knowledge, into the linked network of scholarly research, which is not as easy as it sounds. Because retrospectively assigning digital object identifiers means retrospectively gathering and checking a huge amount of metadata, and I didn't have any resources to do this. Luckily, 2020 was cancelled. In March, our entire scanning operation in Australia was shut down, and with no access to our books or our scanner, we had to come up with work we could do virtually from home. And this gave us a really unique opportunity to improve the discoverability of our existing content online. During lockdown in 2020, our BHL staff and volunteers collected article-level metadata or corrected messy metadata that we were able to scrape from websites or download from catalogues. And we did that for over 30,000 articles that were online already but were not discoverable because they lacked that article-level metadata. I'm going to talk to you today about 3 of those articles, 3 of those 30,000 articles, 3 platypus, that were until very recently lost in that sea of literature online. The first is from the Proceedings of the Zoological Society of London. Here it is on the Biodiversity Heritage Library website. Notes on the duckbill, Ornithorhynchus andatinus by Dr. George Bennett. Our version is open access, as it should be because it was published in 1859. There's another version online on the Wiley Online Library website, but it's behind a paywall. If you want to download and keep a copy of that article, it'll cost you $49 US. Wiley has assigned a DOI to every single article all the way back to volume 1 in 1830. And because their versions have DOIs, that makes their versions the definitive versions that everyone must cite as part of that linked network of scholarly research, which makes it doubly upsetting that they charge for access for this out of copyright content. But I'm not here to talk about ethics. I'm here to talk about retropids and discoverability. It's great that Wiley is retrospectively assigning DOIs to historic articles. However, when I searched for this article, this platypus article on the Wiley website, I had a lot of trouble finding it, and not just because they charge for access. I had trouble because the only metadata that Wiley has attached to this DOI is the date and the name of the person who chaired the meeting on that date. Now, these are proceedings of meetings. And that there, June 28th, Dr. Gray, is the meeting level metadata, not the article level metadata. That's this, the titles of the scientific papers and the authors of those scientific papers that were presented at those meetings and subsequently published in the proceedings. That article data is missing from Wiley's DOIs. So if you're looking for information about the platypus, you're not going to find this article. That's the altmetric wheel for the article, measuring the citations and the sharing of this article. It's blank. It shows 0 readers and 0 sharing of that article ever, which is a shame. During 2020, we worked through all the back issues of the Proceedings of the Zoological Society of London, and we manually collected the article metadata going through those pages in the Biodiversity Heritage Library website. We found that at that one meeting of the Proceedings of the Zoological Society of London, that meeting in June 1859, there were 15 scientific articles presented and subsequently published. None of this article level data is on Wiley, and thus all these articles were undiscoverable. We've now added the article level metadata to BHL, which means that these articles are discoverable not just within the BHL website, but also via external search engines. But they still don't have DOIs, which means they still sit outside that linked network of scholarly research. My next step will be to contact the Zoological Society of London and to ask them whether they would consider allowing us to assign DOIs to the versions of these articles on the Biodiversity Heritage Library website. That would ensure that they remain open access. However, I'd be quite happy to hand over our hard-won metadata to Wiley if they made their versions open access too. So stay tuned. I'm now going to take you a little further back in time to 1832. This article is from the Philosophical Transactions of the Royal Society of London. The illustration isn't quite as cute as the last one, but it's incredibly significant because that is a mammary gland. This is the article in which Richard Owen in 1832 confirmed that the egg-laying platypus is indeed a mammal. The Royal Society of London have all the back issues of their Philosophical Transactions on their website, and they've assigned a DOI to every single one. And their metadata includes the titles and the authors, which would make this article discoverable if it weren't for the fact that there's a spelling mistake in the scientific name. Now, they've done what a lot of people do when they're dealing with historic content, and that's that they're relying on the OCR. This is an OCR error. Their optical character recognition software has picked up that H at the end of Ornithorhynchus, and it's read it as an L and an I. So the title there reads Ornithorhynchus. And that means that anyone searching for this information about the platypus is not going to find this article. Again, there's the altmetric wheel for this hugely significant article. It's blank. We've now added the article level data for the article to BHL with the correct spelling for Ornithorhynchus. And this means that readers searching for this article will be able to find it both within BHL and via external search engines. And because this article had a DOI already, we've included that DOI in our article metadata, which links our version to the definitive version of that article on the publisher's website. And we do that because a DOI is a critical part of an article's bibliographic metadata, and it should be included as a clickable link in any mention of that publication, a critical clickable link. Finally, I'm going to take you back in time to the very beginning. So this article, published in 1799 in the Naturalist Miscellany, is arguably the most important platypus article of all. This is the article that introduced the platypus to the world, its international debut, the first published description and illustration. The Naturalist Miscellany contains scientific descriptions and illustrations of over 1,000 species that were sent to London from around the world in the late 1700s and early 1800s. Finding and citing the descriptions in this publication has always been particularly difficult because the volumes lack page numbers. And until very recently, the descriptions online lacked both article data and DOIs. This is Chris Healy, who's our BHL Australia's digitisation technician. He normally does all our rare book scanning, but he spent 2020 adding article level metadata to all our rare books, collecting that data from scratch. But it was work that was well worth it because so many of Australia's iconic species were described for the very first time scientifically in those pages. We're now in the process of uploading all that article level data into BHL to make sure that these species descriptions and their beautiful illustrations are discoverable. And we're assigning a DOI to every single one. Those DOIs will resolve to the freely accessible versions on the Biodiversity Heritage Library website. And I'm so completely thrilled that the platypus and its friends are now part of that never-ending chain of knowledge. And now that that platypus has a DOI, we can track whether people are using and citing it. The article has only had that DOI since October, but its altmetric wheel is already looking pretty impressive. If you click through to get more information about the DOI, you'll see that the new DOI appears on 5 Wikipedia pages, it appears on a blog, and it's been tweeted or retweeted by 201 individual, 201 individual Twitter accounts with an upper bound of over 700,000 followers. So it seems that I'm not the only one excited about retropids. My initial tweet about this new DOI got some pretty enthusiastic responses. Both the idea of this, DOIs for all, and its actual content, absolutely brilliant. The description of the platypus is just fantastic. Good to know that an article published in 1799 can be assigned a DOI. Links like that are essential for citations and cross-referencing. It's new to me that the Biodiversity Heritage Library gives a DOI to its papers. Really cool, because it follows that the web of citations becomes so much more complete. And now that we need this for every other species in order to finally get non-taxonomists to cite our taxonomic papers. Before I finish, it's worth mentioning that not everyone gets their biodiversity knowledge from journal articles. Most people get it from Wikipedia, but that for me is the most important reason why the historic literature needs DOIs. Wikipedia has this automatic add a citation function. All you need to do is paste a DOI into that box, and all the bibliographic metadata attached to that DOI is dumped beautifully formatted into a citation. And that's all I had to do to add that citation to the illustrator's webpage or Wikipedia page. Frederick Polydor Notter is now linked to that DOI. Wikipedia is an incredible resource, and that's because of the tireless work of Wikipedians. DOIs make their amazing work easier. And that's the point of DOIs. They make it easier for everyone to find, cite, link, share, and track scholarly content. This is my final platypus article. It's an historical insight into population changes of the iconic platypus across time. In the article, the authors state that evidence for decline in abundance and distribution is critical, and it's possible only through the inclusion of historical information. And this is why the historic literature so desperately needs retropids. I want to thank you all for listening. Again, I'm really sorry I can't be there in person to answer any questions that you might have, but please do get in touch if you do have questions or if you want to reach out about retropids. Contact me via email or via Twitter there, or even via my ORCID, my own personal persistent identifier. Thank you again.
What a fantastic presentation. I just love learning all of that about the platypus. And I do wish Nicole could be here so you guys could ask her some questions, but hopefully you can reach out to her. And I guess that's sort of I don't know that problem's the right word, but going international, it's hard to accommodate all time zones. So next, now I'd like to introduce Marie-Elise Lecoq, Administrative Coordinator for the Living Atlases community and developer at VertNet, to tell us about the Living Atlases community. Marie-Elise, I'll turn it over to you.
Yes. Hello. So I'm Marie-Elise Lecoq. I'm the Living Atlases Administrative Coordinator, and I'm here to talk about a little bit about the Living Atlases community. So first, what is the Living Atlases community? So it's an open community around the Atlas of Living Australia platform. And what is the Atlas of Living Australia? It's a collaborative digital infrastructure that pull together Australian biodiversity data from multiple sources, making it accessible and reusable. You will find more information on the website. But what is really important for us is the technical part of the LA. So they have a really powerful infrastructure with multiple components. And all of the participants of the Living Atlases community decide to use this infrastructure for their own data portals. So I'm going to explain a little bit more about that. But first, sorry. Oh, sorry. So first, I'm going to give you some key points about the community. So everything starts in 2013 when the Living Atlases of the Atlas of Living Australia and the Costa Rican GBIF node decided to do a project together. And they organized the first international and technical workshop around the ALE tools. In November 2014, the GBIF Spain launched the first data portal based on ALE. And since this date, around 25 data portals in production has been launched, and we organized around 10 technical workshops, and we manage at least 8 funding projects. The Living Atlases community has a ALE Slack, GBIF node developer Slack, where you will be able to ask any technical question. Today, there is more than 100 members, including the ALE technical team, and every month, new member comes. And one of the most important parts is that the data portal are available in many languages, and you will be fine. If you follow this link, you will find the different language available. So the community is a worldwide community. In green, you will see all of the countries that have an institution that hosts or develop a data portal based in LA. And in a light blue, it's the institution, the countries that host institutions that are currently working on a data portal based on LA. But before everything, the Living Atlases community is a community of people, meaning that we are developers, mainly developers. There is some manager, but mostly developers. And the main goal is to help each other using different communication tools. But it also means that the developer will use the LA platform, but they may, they may improve the tools or develop new features. And those new features and improvements are sent back to the main project. For instance, a couple months ago, JB Friends made a small improvement. It was only create a previous and next button on the occurrence page. And in one of the last version of the LA platform, you can see now this new feature. So it's really working together. But so the community really starts in 2013, but the first couple of years was to be sure that we will be able to use this platform for our national or thematic data portal. Since 2 years, we decided to go a little bit further. And for this, the JBIF and the community decided to hire an administrative and a technical coordinator. So I'm the administrative, and Vicente from who also work at JBIF Spain is a technical coordinator. We also put in place community management, and it's composed of the participants of the LA community, but also from people from the JBIF Secretariat and both coordinator. And the main goal is to help define the future of the LA community in terms of projects, funding, and what we want to do. And it also defines the task for both coordinators. But the community won't work without a good communication. So there is 3 different types of communication. So the first one is what I will say more the technical communication. So it's everything around the LA platform, so the technical documentation that you can find on the wiki, the Slack channel that I talked before. There are also the website, but the website you will find more about the presentations that we already did, or information if you are interested by the project, if you want to contact the administrators, the coordinators, and etc. We have our Twitter account and also the mailing list. The mailing list is more for non-technical questions, as we have released a Slack channel for all of our technical questions. Oh, and if you want to be added to the Slack channel, if you're interested by the tool and you want to be added, just contact me or Vicente, and we will add you to the Slack. So in order to help the participants, because we know that the Atlas of Living Australia toolset is really complicated. Let's be honest, it's a complicated platform. But since a few years now, and since the technical coordinator, several tools have been put in place to simplify the configuration, installation, and maintenance. If you decide to use the LA platform as your data portal today, it's way easier than 5 years ago. So the first tool that I'm going to talk is the generator Living Atlas. A Living Atlas is just one data portal. It's a generic word that we use instead of using the name of each data portal. So the generator Living Atlas is a utility that helps developers to create initial Ansible. So Ansible, it's a software that helps the deployment of an application. I'm not going to go really far on this part, but I invite you to see the presentation made by Manash Shah during the TED Week 2020, where you will see a little bit more information. You will learn a little bit more information about these tools. There is 2 versions, the web version and the command line. So both this slide and the next one come from the remote support session for the Living Atlases portal deployment done by Manash during the TED Week. So this is the website, and this is the command line. So as you may see or not, it's really easier now because it's question and you answer yes, no, you give information like your domain name, and at the end, your Ansible script are generated. But if this tool is not enough, we put in place what we call the remote sessions. So the remote session, it's it's a remote session, sorry. It's conducted by the technical coordinator. And the main goal is to introduce what is the LA platform. You will be able to bootstrap a test version, or you will be also able to test your production deployments. You will find more information on this link. And there is some example of data portal installed with the support of a remote session. For instance, the Biodiversity Atlas of Australia, the Vermont Center for Ecostudy in Vermont, and the CONAP in Guatemala. But we also have a data portal who are not in production yet. For instance, in Tanzania, we work a lot with remote sessions. And then we have the second type of communication, and this is more focused on end user. So this is participants who develop exercise tutorial videos to help their own user to use their data portal. Each exercise in several languages. For instance, the Biodiversity data portal of JB Friends, you have 2 tutorials in Spanish and in English. Canadensis did the same in English and in French. Canadensis is one of the first participants who decide to go from an old data portal to the Living Atlases, the Atlas of Living Australia platforms. So they did a tutorial to compare both tools. We have also a tutorial video in Portuguese done by the Brazil GBIF node, and obviously the Atlas of Living Australia user guides. And then we have the third communication aims to people outside the community. The main goal is to explain what is the community and what is a living atlas. So we made 2 tutorial videos. One to show how to search and download data, and the other to show what is spatial and what are the spatial and region models. Both videos are using a generic data portal, so it's what we call the World Living Atlas, and it's just the first step to know about the project. But last year, during the working session, the Tadweek working sessions, we organized a workshop, and it's the first time we did a session just with live demonstration of 7 data portals around the world. So you will be able to see a data portal in production using the Atlas of Living Australia. So concrete examples of what we try to do since 10 years now, almost 10 years. So you have a link to the video, and if you have any question, we have a file where we put all of the notes from these sessions. So thank you very much. As I said, this is the link that may be interesting for you. First, the Slack channel. We have our Twitter account and our website. And if you have any question, you can send me an email to me or to Vicente, the technical coordinator. You have both email at the end. Anyway, thank you very much for your attention.
Thank you so much, Maria-Elise. That was excellent. I think we might have time for one quick question. There is a question in the chat if you could post a link to one of the data portals in production. But if anyone wants to ask a question, we have time for a quick question now.
If you go to the website, there is on the homepage, at the end of the homepage, there is a link to all of the data portal in production.
Okay.
But I'm going to add this link
to
the chat.
Awesome. Great. Okay, well, we'll have time for more questions and discussion, a little bit of time at the end. So you guys can be thinking of questions that you want to ask Maria-Elise then. Next up, we have Dr. Nikki Nicholson, Senior Research Leader in the Biodiversity Informatics and Spatial Analysis Department at the Royal Botanic Gardens, to share with us specimen duplicate detection in aggregated biodiversity data. Take it away, Nikki.
Hello. Yes, so I work at the Royal Botanic Gardens Kew, and I'm going to talk about how we've transitioned our specimens from physical specimens to a digital representation of them, to an aggregator, and then we make links between the records in that aggregator. So the examples are botanical ones, but my background is a computer scientist, so I'm more interested in the data than the physical specimen itself. So hopefully it will be translatable to this audience. So first we'll look at what our collectors do in the field. So botanical collectors, primarily because plants can't run away, they can collect multiple specimens for a single collecting event. And they will share a lot of attributes. They'll represent the same specimen, and they will be collected at the same place, the same time, by the same people, growing in the same soil, subject to the same habitat conditions and so on. So they share a lot of data. But these multiple specimens are then posted out to separate repositories around the world. And on the right, there's a picture of the Kew Herbarium, which does make me a little homesick because we're all working from home and I'm not in this fantastic building at the moment. But here we can see there's a whole set of specimens laid out there for scientists to come and consult and work with and annotate and use as the basis of their hypotheses. And the story doesn't end there. When we bring a specimen into the collection, then we have a whole load of events which happen after that point in time. And we can kind of characterize these into two kinds of events. We've got a whole set of events that are about the research use of the specimen. So scientists will look at the specimen as it's been preserved for long-term storage, and they'll identify the species which is represented on there. They'll annotate it. So in botany, we press our specimens flat, as you can see in this image here. And we've got then a big sheet of paper on which we can write and make notes and paste labels. So this is a very data-rich specimen. We can sample DNA from the specimen. We can make measurements of the structures. We can assert whether the specimen was in flower or fruit at the time, which is useful for climate change studies. And crucially, we can cite these specimens as the basis of research. So my example that I'm walking through here is a specimen that was collected in the 60s, but in 2010, it was used as the basis of a new species description. So we've got a very long-term use of these specimens through time and as our scientific understanding is increasing. We've also got a lot of processes that we conduct that are about the information management of the specimen. So we image them, and again, because they're flat, they image rather easily. We can do metadata capture, so we can transcribe all the rich data that sits in these different labels on the specimen. And we can do metadata enhancement. We've got a huge set of specimens which have been collected which predate handheld GPS. So we have to convert descriptions of fine spots where collectors worked in the field into computable points so that we can do analyses with them. And crucially, we're doing these kind of activities in all the different collections across the world. So we're aggregating those data together. We're representing the data in data standards like Darwin Core, and we're sharing them with aggregators like GBIF, as we heard in the previous talk. So these post-collection events, we can characterize them as being distributed, happening in many different places, happening in parallel, and often the results of these are unreconciled. So we know that our specimen collectors in the field pick up multiple specimens. They've got independent lives in different collections. We want to make links between them when we see them together in aggregators. So I'll just walk through the kinds of data that we have about the collecting event and how we could do that. This is the same specimen as the previous slide, but I've just focused in on the collecting event data that's on the label. And this is the classic kind of what, where, when data. So we know what was picked up. It was a solanum. As I mentioned, it was picked up in the 60s, so no handheld GPS. We just got a description of the fine spot. We know when it was collected. We also know who collected it. So we've got a description of a collector team and their number. And we know why it was collected. So they presumably conducted quite an intense period of field work over a couple of years as an expedition to the Andes. This data that I've shown today, it's all text data. And for purposes of being easy to make an example, I've picked a typewritten label. They're often handwritten and they're often really difficult to read. So there's often quite a lot of interpretation that happens between reading the label and turning it into digital data that we can work with computationally. That said, we do have a couple of numeric parts of data. So when collectors work in the field, they each assign a collector number to their collecting events, and that helps them tie together the physical material that they pick up and the notes that they make in their field book. So all those things can be tied up together. And this is entirely self-managed. So Paul Hutchinson has put 5738 as his collector number on this collecting event. And he will send that sequence as he does his work. And we've also got the date, which we can represent numerically. And right at the bottom, I've just highlighted, there's a reason why it's good for us to resolve duplicates. So at this collecting event, he picked up enough to make 11 sheets. And he sent those 11 sheets to many different herbaria around the world. And when they get into GBIF, they're all going to be separate and we're not going to know which one's which. So focusing in on what we use for duplicate detection, When this is done as a human scale process, which is the kind of thing botanists would do as they're working with specimens and trying to find out where they are and what they could easily consult, they would traditionally use transcribed data. So they would use the collector name, the collector number, and the year. But when we start to move into larger scale data sets, that becomes really quite difficult. So I've just listed out here, just from the top of my head, half a dozen different ways that we could represent the name Paul Hutchinson. And they're all perfectly valid within the context of one's own collection. But when we bring together huge collection data sets from different places around the world, there's a lot of variability, and it's difficult to know which one, that these all represent one single person. So the approach that I took was to sidestep the use of transcribed text data and use only the numeric components to detect collector activity. So we know that Paul Hutchinson is using a collector sequence, and he's ascending that sequence through time. As he continues through his field collecting career, he's moving forward in time and he's ascending his sequence. So I've got a few plots which should indicate how we could do this computationally. On the left, I've made a plot of data from GBIF where I've pulled out collecting events which have an event date to the granularity of day. And on the y-axis, we've got record number. So we can see with our eyes, there are some long elongated traces, which we could hypothesize are collector activity traces. People are moving forward in time. They're ascending their own personal record number, even though those record numbers are being used also by other collectors. The incremental trace is kind of characteristic to that person and how they're, at what speed they're conducting their collecting career. And in the center, I've isolated out a subset of collecting event data where I could pull out just someone who had an unusual name. And we see that we've got collecting activity as quite a punctuated activity. In the bottom corner, we've got quite an intense period of allocation of collecting numbers. Then we've got a couple of months probably where this person didn't do any field work, back in their institution writing a grant or something. And then they're off in the field again and they're assigning collector numbers again. So we see this trace of work, somewhat punctuated, but it should be characteristic of a single person's work. The last plot, plot C, shows the results of a DB-scan clustering algorithm that was run on the collecting event data. And this shows that the clustering algorithm, which can find long elongated traces as clusters, has found, I've shown here the top 3 most numerous collectors. And it's found collecting traces which cross, and it's allowed us to assign different specimens to a particular collector, even if their collector names have been transcribed in very variable and different ways in different digitization processes. We still managed to assign them to the same collector ID. So armed with that, we can look at aggregated data and we can total them up and we can find groups of specimens which arise from the same field collecting event. So obviously I've had to kind of rush through that process a little. So there's a pointer to the publication which properly outlines it there. I'll drop that link in the chat later. And with GBIF, we've been working on implementing this within the GBIF data portal itself so that we can navigate more easily between duplicate specimens and we can kind of start to group up data within the aggregated data resource. So this makes duplicate detection quite a trivial exercise now. We've got purely numeric data on which we can group. We can group up collector ID, event date, and record number, and we can pull together those 11 sheets that we showed in the example to get a specimen group that all came from the same collecting event. We can then look, and there's a reference to another paper, how we can group together those data and across institutional boundaries share the kinds of products that we make post-accession. So if we do georeferencing work, which is expensive and quite fiddly, we could share that between different institutions. But we can also step right back and we can say that the specimen groups and the places in which those specimen groups are shared could help us have a high-level view of the connections between different institutions And we did this using network modeling. So the building of a network model of the institutions in botany was done just following these three steps. We made institution codes, the nodes. So here I've shown Kew in New York. We built a relationship between the nodes if the two institution codes co-occurred in a specimen duplicate group. And we weighted it. So every time we saw those two institutions co-occur, we just incremented the weight. So you end up with a weighted graph, which represents the strength of the relationships between different institutions. And then we can run community detection on that graph. This means we could find communities that seem to closely share sets of specimens and could then work more closely together across institutional boundaries on activities like georeferencing or understanding how to interpret the handwriting of particular collectors, those kinds of things. And I've just got a quick visualization of the graph. I won't go into the details of it for a non-botanical audience, but the communities that we found did map to the communities which we would understand that exist within our science. So for example, the green set of nodes on the left-hand side represent the consortium of Californian herbaria. At the bottom, we've got the set of Australasian herbaria, Australia and New Zealand. And at the top, we've got a big mixture of nodes between Brazil and the herbaria in the global north, in Northern America and Europe. And this represents the effort that Brazil made to digitize their material where it was sitting in the colonial countries, and trying to build a virtual herbarium from that. So we can start to see the reasons why we have links between different countries and different institutions there. We can also step back a little further, and we can use this kind of data to make predictions about data which is not yet digitized. So this final slide, this shows us the output of a single collector's career. And at the bottom, I've laid out the institution codes in which we found the specimens that she had collected. And on the y-axis, we've got the record number. And if the bars are colored in, then the record has been digitized. So this collector, in her career, she conducted around 8,500 collecting events. And they're primarily digitized in BR and K. But the Smithsonian, the US, does have some represented, and there are scatterings of collections in other organizations as well. We can see in the center that K has comprehensively digitized between 5,000 and 6,500 collecting events to the mid to the late of her career. And we could hypothesize that those specimens probably also reside in BR. They haven't yet digitized them, but Q could post out that data to BR and could help them facilitate their digitization processes. So hopefully I've shown that our data are incomplete and they're heterogeneous. They've been built at different times and they've been digitized to different individual institutional data standards, although we represent them in a common data standard, Darwin Core, when we present them to an aggregator. And in that aggregator, we now have a critical mass of collections data that we can use to detect patterns. We can use these to uncover human scale patterns in specimen collection. And that can really help us with the post-accession processes that we conduct on the data using things like georeferencing. And we can also kind of data mine out implicit entities. So we've always acknowledged that we have things like collectors and teams, and collectors and teams conduct things like expeditions, but we've not really formally managed those within the data. We can use these to get a higher level view of the collections landscape. And we can also better understand the relationships between organizations that hold specimen collections. And personally speaking, as a computer scientist, this data, the fact that it exists in such a volume with such motivated experts, makes it a really rich domain for applied computer science research. So I've put in a few references and links at the end here, and I can drop some of those in the chat also. There are a few ways to to get hold of me if you've got a question, or we probably have a time for questions now.
Thank you so much, Nikki. That was really impressive. We can take one quick question if someone has one. I see Neil. Neil, do you want to ask your question?
Yeah, simple. Does this complement or integrate with Bionomia and the digital specimen concept?
So with Bionomia, I guess they're kind of crowdsourcing what I was trying to do computationally. So yeah, they should be complementary. I think the work that I did was basically unsupervised machine learning in terms of clustering. So the really valuable thing that Bionomia has done is put human eyes on this data. So we could then test the clusters that are proposed from machine learning approaches with the data that Bionomia has created with experts. So we can, yeah, they're very complementary approaches, I think. And sorry, the second one was about extended specimens.
Yeah, you know, Alex Hardesty and other people promoting or developing the digital specimen concept of having a persistent identifier. Yeah.
So the extended or digital specimen concept is really about the recognizing that we have these physical specimens, but then they have this whole life in the digital realm, and that we are aiming to better build links between them and understand how they're used in, say, in scholarly literature, better citing specimens, things like that. Yeah, this hopefully that contributes a little to that. I will make a plug. There's a consultation running, organised by GBIF, that's going to kick off in a couple of weeks about the extended and digital specimens concept. So I can also drop a link in the chat to that if anyone here is interested in participating. We'd really like to hear from as many people as possible on that subject.
Great. Thank you so much, Nikki. I really appreciate your time today.
Thank you.
And so next, our next presentation is a tag team from Curtis Drierson, sorry, Curtis, computer scientist from Utah State University, and Neil Cobb, ecologist from the Northern Arizona University, and coordinating the SCAN data portal to talk to us about Symbiota 2, promoting fairness in biodiversity databases and developing extended specimen pathways. Give me a second to get Curtis's pre-recorded presentation up.
Hello, I'm Curtis Drierson. I'm a computer scientist at Utah State University. This is joint research with Mary Barkworth, Vishal Sharma, Arihant Jain, and Joshua Webster at Utah State University, Neil Cobb, Evan Dunn, and Ben Brandt at Northern Arizona University, and Will Pierce at Imperial College. This talk is in two parts. I'm going to talk to you about Symbiota 2, and in particular about data standards within Symbiota 2 and the use of standards within Symbiota 2. And Neil is going to talk to you about fairness. Well, Symbiota 2 is a web database application, and it's a rewrite of Symbiota. Both projects were funded by NSF. Symbiota is a widely used database application for managing specimen collection data. Who collects specimens? Herbaria, natural history museums, and others. This map shows Symbiota collections within the United States, but Symbiota is used within other countries as well. Today, I'd like to tell you the story of a data value within Symbiota 2. In particular, I'm going to focus in on the SciName, which is the scientific name of a specimen within the Symbiota 2 database. So life begins for this value within the database, and Symbiota 2 is stored in a relational database. This relational database is somewhat complicated. This diagram shows the MySQL Workbench entity relational model for the database. In this diagram, every node represents a table in the database. The columns within that table are listed in a very, very tiny font. It's impossible to see in this diagram because there's so many tables and the database is quite large within that particular node. the edges between the nodes are foreign key relationships between the tables. And what we're going to do is we're going to focus in on the taxa table. And within that taxa table, we're going to look at the SciName column. And that column is represented by that tiny blue oval right in the middle of this particular diagram. The next step in the life of the SciName is to move the SciName from the database into the front end of Symbiota 2 so that users can see it and edit it and so forth. So for every piece of data within Symbiota 2, we provide two kinds of services, a GET service and a PUT service. The GET service reads information out of the database, providing it to the front end, and the PUT service puts information from the front end into the database, and all access to the database is through these services. In order to support the web services, what we're going to provide is a web service specification. This specification is independent of any particular database management system, so it doesn't matter if it's Postgres or MySQL. It's a high-level specification, given at a very abstract level. And from this specification, what we're going to do is we're going to generate web services from the specification. Now, the specification provides a very important mapping, and this mapping is between tables within the database. These are relations within the database, and objects provided by the web service. The web service maps this relational data, this tabular data, into a hierarchical model. This hierarchical model represents an object, and this is called an object relational mapping system. Now, unfortunately, from a standards perspective, there's no standard for this specification. Instead, the specification depends on the kind of tool that we're going to use. For Symbiota 2, what we're going to do is we're going to write Symbiota 2 in TypeScript. And for TypeScript, there's a tool called TypeORM, so Type Object Relational Mapper. And here's an example of the specification for the taxa table. And in this particular specification, in the middle we see the scientific name, which is mapped to a string in the object. And this is a very simple specification. And it just takes this one table and dumps it out as an object. But from this specification, we can build a web service that provides read and write access to this data. So using TypeORM, we can specify web services, and these web services will provide communication between the back end of Symbiota 2, the database, and the front end of Symbiota 2, the graphical user interface, which is a web browser. And using these web services, we can transfer data back and forth between these two parts of Symbiota 2. Now, the only standard that's used within this web service specification is the OpenAPI standard. And OpenAPI is typically coupled with web service specification tools like TypeORM and Doctrine. And it documents what the web service, the information that the web service provides, and allows for discovery by web service search engines. But thinking more broadly, how can this scientific name value within a particular Symbiota 2 database be connected to the larger body of information that's out there in the world? So how do we integrate Symbiota 2 with other data collections? Well, the first kind of connection we can make with other data collections is that we can export Symbiota 2 data in Darwin Core format. So Darwin Core is a standard format for representing specimen data. In this case, for Symbiota 2, we provide simple Darwin Core data. This Darwin Core data is exported as XML, as shown in this particular diagram. And our scientific name is this particular XML element, DWC:(scientific name. And it is exported within a Darwin Core record, within a Darwin Core record set, and this Darwin Core data can be collected by engines that harvest Darwin Core data. The second kind of connection that Symbiota 2 can make with other data collections is through the export of a Symbiota 2 knowledge graph. Now, the idea behind a knowledge graph is what it's going to do is it's going to glue together information from sort of different communities. Now, if we think back to the Darwin Core example, Darwin Core is a standard for exchanging data within a specific community, the biological specimen collection community. And if we want to market or export a biological specimen, we produce it in Darwin Core format to be harvested by people who want to utilize that information, that knowledge. But communities have different ways of representing their information, different standards. And so how do we glue together all the different standards into a combined whole? Sometimes these communities are independent, but often it's the case that they have interlinking or interdependent information. And a knowledge graph is a way to build connections between these different community representations, these different standards. Now, knowledge graphs are useful, and here's an example of how knowledge graphs can be used, and it's a Google search. And in this Google search, I've punched in Einstein, and the left-hand part of the screen shows a typical Google search where we bring up pages associated with the search for Einstein. But the right-hand part of the screen is a little box, and this little box is information about Einstein Brothers bagels. And this box is produced by the knowledge graph that Google pulls together that has information or data about Einstein's Brothers bagels. So where does this information come from? Well, here's part of the graph that Google builds, or Google uses to build up their overall knowledge graph. So they get information out of Wikipedia, DBpedia, a bunch of different data sources, and they look for connections between these various data sources, between the information provided by these data sources. The connections between these data sources are mappings or so-called ontologies between the vocabularies used within these particular standards, within these particular data collections. So how can we contribute to this knowledge graph that's going to be used by Google and used by others? Well, for the Symbiota 2 knowledge graph, what we're going to do is we're going to use a W3C standard called R2RML. And this is particular R2RML standard. What we're going to do is we're going to take our relational database and we're going to map it to a knowledge graph. Now, this graph is going to be generated, or this graph is going to be represented in the Resource Description Framework, RDF. And here's an example of this mapping. And in this particular mapping, we focused in on the sign name, our little data value. And so this is the sort of the end of the lifetime of our sign name data value. We've exported it out there into the world so that it can be harvested by Google and integrated into Google search. In summary, the life of the scientific name within Symbiota 2 is a little bit complicated. We'd like it to be a simple story, but there's a bunch of different standards involved and a bunch of different ways that the data is exported. It's exported as using a type ORM specification. It's documented using an Open API standard. It's exported into Darwin Core standard that's not connected to the type ORM specification. It's also mapped to a knowledge graph using R2RML. And so the problem really here is a plethora of standards and there's no single specification. I think a single specification would make life easier for everybody, but I don't know of any tool that does that. Thank you.
Okay, Neil, I'll turn it over to you to briefly talk to us about the extended specimen concept. Neil, if you're talking, we can't hear you.
Okay, sorry. So I'm going to provide a domain scientist sort of data user view of Symbiota 2. I'm an arthropod ecologist, and I'm really excited with what Curtis and others are doing in restructuring Symbiota and basically preparing it for this new phase in digitization. So I think Symbiota 2 is going to do two really important things. It'll allow us to make all data fair and create new extensible data. And so what I mean by extensible data is extended specimen data. For the last 10 years in the US, we've focused on digitization that entailed transcribing labels and doing some imaging of specimens. And what I call this new phase of extended specimen, we'll be focusing much more on getting a lot more information out of specimens, like traits, genetics, and then linking that with other types of data, like remote sensing, environmental data, to create these cross-disciplinary data sets that will create a lot more opportunities for research. And I maintain that we cannot move forward on this extended specimen road without ensuring that we've integrated FAIR practices throughout. And when FAIR first came to light, I thought, oh, Symbiota, we do everything that's fair. I didn't really think much about it, but I'm starting to realize, especially moving into this extended specimen era, that it's really, really important to emphasize to data providers. So a couple of examples of how Symbiota 2 will make our data more fair and extendable. Right now, specimen data it'll allow us specimen data records to use all WC fields and extensions. Right now, we only use 90, and it's a real pain in the butt to add any Darwin core field. So this will totally open it up in that respect. Other CMS systems besides Symbiota, like Arctos, can use the front end of Symbiota, for example, potentially using an Elasticsearch dashboard to summarize their data or their queries. And it will make it a lot easier for developing direct API linkages with other databases like BOLD and iNaturalist. I think it will also help us to actively solicit participation by researchers to make their extensible data fair. So there's so much data still being published today, biodiversity data, but for example, specimen data is by these mostly ecology projects, is harvested from collections or data aggregators, but they don't ever link back to specimen data. There are ecology projects that do not catalog all unique events, a unique event being a specimen site and date. And that's, both of these are really, really critical in the FAIR part for making data reusable.
Hey, Neil, if you can go through what you have left pretty quickly so we can move on, that would be really great.
Okay,
sorry.
So here's just one example of a pending project called iDigBees, where we've established workflows, all of the linkages, and we've identified how we're going to extend the data primarily through our processes. And this is just one of several projects that we're going to implement extended specimen work. And I'll just end with this extended specimen workflow. So in the left is the collection, curation, digitization part. This is sort of what we've been doing for the last 10 years. And off to the right are 14 boxes of extensions. And so for the B project, it simply provides a number of extensions that we're going to develop that will, sort of what I think will greatly increase the use of specimen data. And that's it.
Great. Thank you so much, Neil. I really appreciate you running through that quickly. In the interest of time, I think we have to move on, and hopefully I'm hoping we'll have about 5 minutes at the end for questions. So last but certainly not least, we have Megan Cromwell, an oceanographer with NOAA's National Centers for Environmental Information, to tell us about video data solutions, standard biological data quantification, and data accessibility with machine learning techniques. Megan, I will turn it over to you.
Awesome. Let me hide this. Okay, so I'm going to start by introducing myself. I work for NOAA, the National Centers for Environmental Information, but I work on a project called the OER Data Management Team. So I'm the team lead for the NOAA ship Okeanos Explorer, operated by NOAA's Office of Ocean Exploration and Research. And I also have a huge passion for video data. So with video data, particularly deep sea oceanographic video data, we have all kinds of problems. It's usually has low levels of metadata. There's a lack of standardization. It's huge in volume, but one of the bigger issues is that to annotate it, right, because it's qualitative data, to annotate it and make it quantitative, it typically takes about 4 hours for every 1 hour of video. For the NOAA ship Okeanos Explorer, we use those annotations and metadata records to then make it findable. But a lot of video doesn't have that. And so it's really hard to make it discoverable without annotations. So OER, and we have teamed up with Ocean Networks Canada, and they have a thing called CTube. So what this allows us to do is, as we telestream, which is live streaming the video so scientists on shore can participate, they can go in and make real-time annotations while the dive is occurring, or they can come back after the fact and do post-cruise annotations. We've adapted the CMEX standards and the World Register of Marine Species to try to help with standardization, and I'll explain why in just a minute. I'm trying to go a little quickly because I know we're running low on time. So our solution for the Okeanos is that we built the OER video portal. It's tiered storage and access. Basically, it has a Google keyword search that you can search on any of those annotations. It's backed by metadata records that we use an Elasticsearch within a GeoPortal, because I know someone had just mentioned that. We have really, really extensive metadata though. We have timestamped annotations. We have so much data about this particular video data set that we don't within NOAA have for most data sets. We implemented the WORMS matrix because we realized in some cases you might have an annotator who might put in octopus, and then another annotator for another video on a different dive might put in cephalopod. Well, in that case, depending on if it's a student or whoever, if you searched one of those, you would only get one video back, whichever one it happened to be. So we matrixed it with the common names, and you can actually just search by phylum and say, hey, I want to see all the corals in this particular area. So the problem that we have to solve for the rest of NOAA video data and oceanographic video data, we realize that has a potential solution with machine learning. And so most of you are probably already familiar with machine learning and how it works, but basically it requires labeled data. And then you split your labeled data and you train against 70% or whatever it is that works for you. And you train the algorithms to start to identify things. And then you test it against that subset that you held out. And then you keep going until you can apply it to non-labeled data. Our biggest issue, particularly with oceanographic data, is that labeled data. CTube lets us label data, but it doesn't let us tell the algorithms what in that piece of video or image is actually what we're talking about. So CVision AI is a small business that's been funded through the SBIR NOAA program, and they built a cloud-based video annotation tool, and they've pulled in some of the OER data, and it's open source software too, so anybody can use it. And basically it gave us the opportunity to then go in and localize these annotation. It also facilitates analysis. You can export. It's a really interesting tool. They just were awarded a phase 2. So we can figure out how to do the localizations, but then how do we go from here? So FathomNet is a project that was developed initially in collaboration with Mbari and MIT Media Lab along with CVision AI. And it's launching this year, and it's a publicly accessible database that people can run scripts on to actually start training these machine algorithms that can then develop these annotations. They're using expertly curated annotations. I think it's mostly Mbari right now, but we're planning to put the Okeanos data in it. And for anybody that's interested, this particular video was actually showing that already they've been able to train the AI to go in and follow the jellyfish, even when other organisms come into the screen. So a lot of work has already gone into this. So what came next? We're starting to have the tools that we need to start getting there and solving these video data management solutions. But again, that bottleneck is the localized data. Well, for the Okeanos, we have the expert time-stamped annotations, but we don't have the box. So we teamed up with University of Dallas, CVision AI, the MIT Media Lab, Mbari, NOAA's OER, and there was a big summer project called Minuet, Machine Intelligence, and the students came up with this. It was great. And what they did was they took the expert annotations, they went in and localized it, and then they performed their analysis for their summer project, whether it be biodiversity or some people are actually studying just one specific thing. It went really well. So those data are going back and being put into FathomNet now to expand this database. And I will say that they actually, as they launched, will have shells where people can go in and do their own training within the online database. So this has now been expanded. OER and University of Dallas and a few new universities, Bates College and UCSC, are launching it to try to put it out for students in classrooms, because especially in times of COVID, there's tons of data available. This is an opportunity for people to do analysis and to do projects with data that already exists where they can't go collect it, but it can also feed back into expanding this database that we can then train these algorithms on. So University of Dallas and Bates College are both introducing it in their classes this year to test the syllabus. And then they are also working with the UCSC, which is, they're studying the human and robot interactions, as well as what the students will actually get out of this on their own. So what does this all mean? Basically, as we can train these algorithms, we can then produce the metadata to make the data available. As we make the data more available, then scientists can find it and also go in and analyze it, do their science, and then sometimes we can hopefully continue to pull it back into the training base, which then improves the machine learning algorithms. We really hope at some point to get it down to the level of where you could get maybe genus, species really hard in the deep sea, but definitely go down to class and order and whatnot. And so this to me is huge, because we have all this NOAA video that it's really hard to make accessible and nobody really knows what to do with it. And we have this one really specialized case, but not everybody has the resources to do that. And so this would give us the ability to then make that really rich metadata so we can actually get NOAA's video data out there. Because when you look at it, you've got, I'll use Sylvia Earle as an example. She collected hundreds of hours of data and it got used and then stuck in a library somewhere. And we've digitized it now and made it available with the few keywords that we have. But if we could run that data through algorithms to really annotate it well, it'll be revolutionary for video data management. It also will provide quantification. So if we spit out a CSV for every video and we're like, hey, here's everything that was seen in there that was caught by this algorithm, people can just use that and don't have to actually spend the time analyzing the video unless they're really interested in a specific species. So it'll provide new products for us to help serve and better serve the science communities. But then also we're really interested in looking at it for uncrewed systems. So a couple different things. One, a lot of them collect imagery. And so you want to be able to analyze that easier, which we can do, but the goal is to try to make it where unmanned systems can actually identify a new species and say, okay, hey, this is really important. Let me stick with it for a while. And I know that Mbari, one of their goals, particularly to study snot palaces, is they want an AUV to be able to actually identify, hey, that's the species I'm interested in, and follow it for 24 hours so they can better learn about the life cycle and what's going on and how they live and the behaviors that are going on. And so there's so many different applications, but I got really excited because this is a potential solution for all of NOAA, and particularly way further outside the community, for ocean video to be managed and easier to use for everyone. And I think I made it through fast enough. All right, so I want to say thank you to all of our partners and open it up for questions for us or any of the others.
Thank you so much, Megan. That was really exciting, and yeah, I think it's really going to be revolutionary. So yeah, are there any questions for Megan or any of the other presenters? Nikki has a question. Nikki, did you want to open your mic and ask your question? Turn on your video.
Hello. Yeah, I'm interested to know if you could use species interactions to constrain the classes that you're trying to detect in the video. So if you could be reasonably confident that you found an ID for one organism, could you then say the other things around it in the video, we could constrain them based on us knowing that these organisms often are found together?
Potentially. So we're still relatively early on in the process. We're just really getting going. Like I said, we're still really working hard to build out this database. But I know that when the students worked on it this summer, they would run into situations where you may have a timestamp annotation that says, you know, this is a bamboo coral. And they would realize that there's one annotation, but there might be actually 15 there. And so it was easier for them to do their analysis. But as far as the machine learning algorithms themselves, we're still working on training those. So I would assume so, but I will say that I'm an oceanographer and not a programmer. So I will leave that to data engineers, but we have an awesome team that we're working with. So if you have more questions on it, you can email me at megan.cromwell@noaa.gov. And I would be happy to introduce you to some of our partners who may be able to better answer the programming sides.
Great, thanks. There's also a question from Neil. Neil, did you want to ask your question?
Well, it was sort of the same question, but do these videos help inform inventories and prioritizing inventories? So if you inventoried an area where you had a lot of video data and you just did a one-time inventory, then you can link all this other data down to species level.
I'm not saying it can't be done to species level. What I'm actually saying is that in the deep sea, it's hard to do that sometimes because sometimes it's literally just a genetic difference. But yeah, in certain circumstances with species where you could definitely say, okay, yes, it's this, the goal would be to get there. It's just, we know that we typically operate between 250 and 6,000 meters. And so when you get to 6,000 meters, there's a lot of things that kind of can look the same, but you find out are different later. So yes, in some circumstances, but probably not all. I will say one of the other end goals to this is for us to better inform policy and decision-making, but also for exploration purposes, because that's OER's focus with the Okeanos. And basically we can say, you know, this area has been explored, this area, we don't have enough data to say that it's been characterized really well. So to use the data to inform policy and decision-making as far as where future things happen. So there's so many other applications here, but to answer your question, yes, at some point it should be able to get to species level, but we're trying to be patient and know that it won't get species for everything.
Right, what I would hope is it could actually justify spending money to do the inventories to complement that data.
Agreed, and that's, the better we can show use of the data, the better we can show that people can actually get to and access the data. I think the easier it is for programs to argue successfully of, hey, we need to go back here and look at this, or we need to go put money into this. And so working for NOAA, that's obviously something that hopefully the data supports that.
And can I make another point, Abby?
Sure.
Well, I was just, when you were giving your talk, it just made me think about the overlap between what you're doing and what Toke Hoy and his colleagues from Denmark are doing. They're focused in on the Arctic. So they're trying to develop these automated instruments for capturing all this data from really remote places that you can't send people in. So one of them is a camera that looks at flower phenology and the pollinators that land on them. And so they're exploring the same exact thing you're looking at. So I'd love to link you up or link them up with you, you know, and share knowledge. It'd be great.
Please do. I would love that. I'll put my email in the chat.
Awesome. And so we only have a few minutes left, but I do want to open it up. We didn't have any time to ask Neil and Curtis questions. So if you have a question for them or any just general questions, please feel free to turn on your camera and chat with us. We'd love to have a little bit of conversation here at the very end. All right.
Neil,
I guess,
Neil,
go
Neil
ahead,
is
Megan.
speaking and he's muted.
Aha. Thanks,
Good.
Megan.
For Marley, so when I asked how this relates to VertNet, so VertNet I view as a primary aggregator, and they have a very important role. Does VertNet and Living Atlases have any functionality?
No, it's it's not related. I'm working at 50% for the Living Atlases, and the rest of the time I'm working with the VertNet team. It's two separate components in my, but because the Living Atlases are composed mainly by JBIF nodes, we have the same problematic like data standards, and so on, but it's two separate things in my work. And VertNet is not using the ALA platform at all.
Okay.
Okay, great. Well, thank you. I guess we'll close here if no one else, unless someone wants to jump in there at the very end. Thank you guys for kind of a different session at ESIP, for allowing, you know, it's very presentation oriented, which is a little bit different than the rest of the sessions that happened at ESIP. So thank you for attending. I want to say a big thank you to our presenters and acknowledge your nimbleness in changes with our session. So thank you, really appreciate it. If you would like to join us for more discussions around these topics, please consider joining the Biological Data Standards Cluster. There's a link in the chat to our mailing list that you can sign up and join us. We meet on the first Thursday of the month at 1400 Eastern, and our next meeting is next week, actually on February 4th. If you want to join us, we're going to do a recap of this session and then also start to begin work on decision trees and/or best practice documentation for biological data standards. You can join the mailing list, right? I already said that, so yes, the link is in the chat. And there are other ways to stay involved as well, and there's a section in the notes document which provides options for staying involved in ESIP. And if this is your first time attending, I hope you'll come back again and join us in this work. So thank you, and I hope to see you all again sometime soon.